Is really cool. It uses Flash, and at the time of recording, Flash is about to be completely wiped out, obsolete. So I'm kind of recording this ahead of time so that we can still go through and watch this, because I love this interactive. Because we've been going through and we're talking about quantum numbers and what these orbitals look like and how the electrons go into the orbitals and in what order and things like that. But we haven't really seen what it really looks like when you put it all together. Because it's one thing to think about what an individual orbital looks like, but it's another thing entirely to think about what all of the orbitals look like in an atom all together at once. So what this is, it's kind of a game, and it goes through and it gives you a element, and then you get to go through and kind of build it one orbital at a time to see what that atom would actually look like. So for a helium atom, we know the first orbital that we would put electrons into is a 1s. And we know it has principal quantum number 1, so it's pretty small, and it's an s, so of course it's shaped like a sphere. And we know that 2 electrons would go inside of this orbital. Now, what I love about this is it really shows kind of what the electrons would look like. They're moving very, very quickly, to the point where we almost can't even see them. They're moving in random, sporadic locations. This is a simulation, so it does kind of repeat eventually, but it's crazy all over the place, like in real life. But you also see, especially up here, around in here, every once in a while you'll see the electrons kind of jump outside of the area of our orbital. But if you'll remember, the orbitals are just the probable locations, right? So it's possible for the electrons to go outside of the general shape of the orbital, and they do. But eventually they come back in and they kind of stay inside of the orbital most of the time. But every once in a while it'll jump out. It's kind of neat to be able to see that. Also, as I add my electrons over here, it kind of creates an orbital diagram for me. So we would know that this would have an electron configuration of 1s2, and so it shows the 2 electrons at our 1s orbital. Now it doesn't have the s down here as the labels, they're just kind of implying it, but of course we label ours. So that's it for helium, because it only has 2 electrons, not much going on. But when we go to do something harder, that's where things get more interesting. Because if I were to start with carbon, I know it would be 1s2. So I would need 2 total electrons in this orbital. And of course, if I were to try and go add another electron to it, it would tell me no, because every orbital can only have 2 electrons. So the next place I would add my electrons is a 2s orbital. And you'll notice that this 2s orbital is still an s, so it's still shaped like a sphere. But it's also a 2, which means that it is bigger, right? It is a bigger orbital, so it kind of goes on the outside of my 1s orbital. It's kind of like a new shell, a new electron shell. So when I go to put my 2s electrons on here, these electrons become the ones that are now on the outside. And I will say, I don't really like this part of the simulation, because it kind of looks like the electrons in each of the kind of layers are syncing up with each other, and that wouldn't actually happen. Just pretend that they're all moving randomly and chaotically. But after my 2s, I have 2 more electrons to place. I've done 4 of the 6. And I know now that I need to put 2 into my 2p. And we know that there are 3 different orientations for 2p orbitals. There's the x direction, the y direction, the z direction. So when I go to build this, I see that my 2 is about the same diameter as my 2s was, but I also have my different orientations to choose from. And due to Hund's rule, due to the bus principle, we know that these 2 electrons are going to want to go into different orbitals before they start to sync up. And if I were to try and put both of those electrons in the same 2p orbital, it would say, no, all of the p orbitals must be in place and have 1 electron before filling up a second one. They want their own orbital if they can have it, and they can. Okay, so in order to do that, I have to use 2 of my 3 2p orientations, and each of them gets 1 electron, and we can see that reflected over here on our orbital diagram as well. And that's it for carbon. Now, of course, it's going to give us something bigger. We've got sodium this time. So 1s2. My bigger 2s2. I get to use all of my 2p this time because it's 2p6. And even though I'm using all of it, if I still try and double up, like one there, and then go here, it says no, you have to put it in all 3 first. And now it'll let me, in whatever order I want, go through and put those extra electrons in until my 2p is now full. Again, I've got all these crazy electrons moving around, very chaotic. But then I have my 3s, and you can look and see the 3s is so much bigger, right? It kind of encompasses everything that we just did. And I'm only getting 1 electron out here. It's 3s1. So I think this visual right here really shows you why valence electrons are what they are, because they're the ones that are on the outside, right? You can see very clearly that 3s electron going through here because it is the one on the outermost layer. It's the one that's easier to go in, pluck it out, and do things with. Whereas this 3s layer, this 3s orbital, kind of shields everything from the inside from the outside. It's much harder to get through the 3s and then go all the way down into the 2s. So that is it for our sodium. And then this very last one, I think, is just the full thing, using all of our orbitals, because it's argon number 18. So 2p6. Still got to do these in order. And now I can double them up. Ooh, wrong one. 3s right here. It's going to get 2. And then I've got my 3 orientations for 3p. And I still need to follow Hund's rule. It's still going to be 1 on each. But I am going to have 6 here. It's a noble gas, so it's going to fill up this entire layer. 3p6. And we can see that it has its 8 valence electrons. And if I were to add 1 more electron, that would bring me up to 4s. So I would have a whole new layer out here. It would be a much bigger orbital, and I'd have all of those smaller ones down inside of it. And after my 4s, I'd end up with my 3ds. And of course, we know that since that's quantum number 3, it would bring us back down to this kind of layer. So I'd have this 4s out here super big, but then the 3ds would kind of go back on the inside. So that's why those 3s don't count for your valence electrons, because they're not on the outermost shell. So I hope this kind of shows you how complicated the atoms really are once you put all the orbitals together. I hope it gives you some sort of visual. I know I'm a visual learner, so I like to see it like this.